What service provider series would be complete without a discussion of MPLS? In this nugget, we're going to look at what MPLS is, how it works, and then watch it in action. Here is your Do I Know This Already question, so review those. If you know them, feel free to move on. Well, let me start off with a question. How many of you have heard of CEF, Cisco Express Forwarding? Show of hands. Oh, a lot. Okay, lot of people. What is CEF? Well, it's an optimization method that Cisco created back in the day. I'm talking like 1999, 2000 kind of time frame to optimize how routers move data. It's an evolution. It all started, when in the beginning, when Cisco created the router, it all started with process switching, which means every single packet that comes into this router, let's say you get a packet that comes in there, it comes into the router in the data plane. The router flips it up here to the control plane, which is where the routing table exists. Think of the control plane as the brain of the router. It's where your routing table exists. It's where your routing protocols work. When you SSH and manage your device, you're dealing solely with the control plane because it's where the thought goes into the router. It's where the router takes the biggest hit in the processor. So this packet would come in. It would say, hey, I've got a packet here for such and such. It would get moved up to the control plane. The router would look it up in the routing table. Oh, okay, well, we've got to send you here. So it would send it back down to the data plane, change the headers, all that kind of stuff. That was process switching way back in the day. Well, they improved it with fast switching, which did the same thing, but it only did it for one packet for each source and destination pair, which was a major improvement over process switching. Well, what Cisco did was come out with CEF, which revolutionized things. They said, you know what? We don't even have what's known as the packet one problem because we are going to pre-cache the entire routing table down here in an optimized space in the data plane to where routers just operate extremely fast. But that was, 14 some years ago now. The rest of the industry has caught up. Juniper has Jeff or whatever they have. Hewlett-Packard has Hef. They've all got their own little flavor of CEF to help them do this. That was the original thing that MPLS was known for. It was often called CEF for the masses. Why? Because MPLS takes every packet that comes in. Let's get a little more scenario centric. Let's say we've got a business over here, 10.1.1.0, communicating to a business over here, 10.1.2.0, through the service provider using Metro Ethernet. What's MPLS do? Well, what it does is as the packet comes in, it says, okay, my source is, let's just say 10.1.1.50. My destination is 10.1.2.50 in that little packet. Maybe it's just a little ping, right? You've got all your normal stuff that's in the packet, the transport layer, the IP layer, source and destination IP address and all that. And then right here, hang on. Right there. MPLS puts in a little shim. I said shim. Everybody's like, what's that mean? A shim. Haven't you ever gone to Home Depot or Lowe's? They sell these little things. They sell them in like packs of 10 little pieces of wood that are cut exactly like this. Anything crooked in your house, like your refrigerator, kind of rocks back and forth, jam a shim under it. My laundry machine, when it goes on the spin cycle, jam a shim under it. The shims are life-changing, and that's what the MPLS network does, is as it comes in, the router assigns, instead of a shim, they decide to call it a label, but really it's just a knockoff of shims. They put a label in the header of that IP packet, which is just a layer 2 number. What do you mean by that, Jeremy? I mean, right here at the very front, you've got your normal layer 2 stuff, MAC addresses, Delcy numbers, VPI, VCI pairs. Whatever this is, what is it? Is it a frame relay connection, ATM? Is it Metro E? It could be anything because MPLS works with anything because it keeps the normal layer 2 header, whatever addressing you're using and network type you're using up there, working just fine. It just puts the shim right after it between the layer 2 header and the layer 3. Here's your IP address stuff that it calls a label, and it just makes up numbers. That's really what MPLS does. Is when you turn it on, which you're gonna love it. The configuration in this nugget is one command to turn on MPLS, and the router just does the rest for you. It looks at the routing table right here and generates labels for all of its route. It's like, oh yeah, 10. This router's like, 10.1.2.0. I know that guy. We're gonna give him label 53. Right? And 10.1.1.0, yeah, we're going to go ahead and give him a 590 92. That's when you don't pre-plan your numbers, they look like that when you write them. So the router just assigns these things little layer 2 labels, and this is why MPLS sometimes originally was called Ceph for the masses, is because now it can keep all of the processing down at that layer 2. Now when a packet is sent, the very first router that it comes into says, oh, okay, well I'm going to assign label 592 to that route, and as it sends it down in the network, all these routers do is look at their label table. And we'll talk more about that later. I don't want to get too far ahead of myself right now, but it just moves all that processing down to optimize it very quickly. Back when MPLS first came out, people were like, oh, MPLS, it's Ceph for the masses. It's industry standard stuff because performance was its major selling point. It's going to improve the performance of your network. Well, not so much anymore. Why? Because things have gotten faster. Everybody's copied Ceph and made their own little offshoot of it. So now people don't look at MPLS and say, oh, it's because of the performance. What it's good for now is that shim provides a level of separation of everything else. Meaning, you can do processing of routes and isolate your customers from each other. I mean, you combine MPLS with that multi-protocol BGP. I think we talked about that earlier in the series. But by combining those two together, you have an optimized, meaning very fast, and isolated way of marking this traffic apart from each other without the routing table ever being referenced. Does that make sense? So a packet comes in, 10.1.2.0 is the destination. Our router slaps a label in front of that. That's our shim that says, okay, well, that's 30, right? Now the routers don't even look at the route anymore. They just look, oh, 30. 30, 50, 90. We'll see more on how this works, but that's the big picture. Let me show you what an MPLS label looks like in my little square world. This is the front of the packet, right? The front is on the left this time. Layer 2 header, it's MAC addresses, it's Delcy numbers, it's whatever network you are using because MPLS works with any of them. And right behind it, this is our shim, right? If it were a triangle and wedged under a refrigerator, it'd look like that. In that shim, you have the label itself, which is 20 bits of information. So it can be a rather large number. You have what's called experimental bits. There's only 3 of them. 1, 2, 3. So how many numbers can you have with 3 bits, decimal numbers? 8, right? Think back to your subnetting days. 8 bits. This actually is nowadays used just by about every vendor as a type of class of service. If you get into quality of service, you find out that there's different markings that you can put in the packet. So I can say, well, this MPLS packet is coming in with an experimental bit marking of, let's just say, 2 in decimal, right? What does that mean? Whatever you want it to mean. I mean, you can create your policies to say, oh, it's a 2. Oh, I want to reserve like 50 megabits per second for anything marked with 2 because 2 is the golden marking of the service provider network. Or you could say, oh, it's a 2. I spit on 2. 2 is like peer-to-peer file sharing. I despise 2 packets. It's whatever you want because you are the service provider. You are the architect of the network. You define what 2 means. So you're going to have a little spreadsheet going on where you've got 0, 1, 2, 3, 4, 5. And you're going to say, okay, well, 2 is actually, and by the way, you're not on your own with this. You don't have to just be like, well, I think 2 is good. I mean, there's industry standard. 2 is usually considered a mission critical data or database traffic. It usually ends up flagged with 2. 3 is like voice over IP signaling, those kind of things. 5 is like voice over IP, real time traffic video. Video usually squeezes it. I mean, there's. I don't want to get into all that. I'm just showing you that it's there. That's what the experimental bits do. Is they're used for quality of service markings, and then you determine how to treat those markings. I mean, it's just like painting a packet red, right? What's a red packet? Well, it's a red packet until you decide that red packets are prioritized in your network. Bottom of stack. What does that mean? I can have many levels of MPLS labels. I can squeeze a label, a label, a label, a label, a label. So as I come in, maybe I initially label it saying, okay, well, this label means that 53 actually maps up to a customer because customer 53 is really Nabisco, and so I'm going to make sure that it ends up in this multi-protocol BGP table, this extension. And then I'm going to put a label after that that says, okay, well, 64 is the route that Nabisco is using. So I can squeeze a whole bunch of MPLS tag. It's not normal to have a whole bunch, but 2, 3, that's kind of normal. And you need to know which one's the last one in there. So as it starts peeling off labels, which it will do, you can have the very last one be marked as the bottom of stack, meaning there's no labels behind this. And then finally, TTL, time to live. Same thing as in the IP header. It helps prevent loops inside of a service provider network by saying how long this packet can live as it goes from router to router to router. So now let me come back to this diagram and talk a little more nitty-gritty. How does this work? When you have a router that is receiving traffic, well, I mean, it could be from a customer, it could be from anything. The very first router that is on the edge of the system gets that name, Edge LSR. That stands for Edge Label Switch Router. That's the term of a router doing MPLS. It's kind of its designator. So inside, what do you think these are called? LSRs, right? Label switch routers. They're not on the edge. They're doing their MPLS deal. Now this one sitting at the edge, and right now you're like, all right, Jeremy, I got it. It's an edge, right? Edge label switch, right? So you got it. So this guy comes in, puts the label on. This guy is the one that is sending without a label. Now, I know I'm being very pronounced in what I'm saying. What do you mean? It means as it comes in, this guy puts the label on. It says, okay, well, I'm going to label this 53. Why? Because this guy, well, actually, let me go the best route. This guy told me that 10.1.1.0 is really 53. What do you mean? I mean, every single one of these routers generates its own label table. I mentioned that a little earlier. It actually goes into something called LFIB. Again, I've got slides on each one of these things, so just keep these right now in the 10,000-foot view perspective. But this guy generates all these labels, so he has a table that says, okay, well, 10.1.1.0 for me is 92. That's my label, right? So think of it just like an Excel spreadsheet, right? With all these different networks. So you have the network and you have the label sitting right here next to it. The key is that these routers start exchanging their label tables. So router 2 over here tells router 1 about its label table. So router 2 says, oh, well, 10.1.1 for me is really 62. This guy, we'll say router 3 over here, says, oh, well, 10.1.1 for me is 53, right? Thus, as this guy comes in here, and I got to, so this guy is 10.1.1.2. This guy is 10.1.1.1 now, or 10.1.0. So as it comes in saying, I'm sending to this network over here, he's going to go, okay, well, I have to go this way to get there, so I'll put label 53 on it. Why? Because router 3 told me that it assigned label 53 to 10.1.1.0. And I want to make sure when router 3 gets the packet, he doesn't have to look at his routing table. He just looks at label 53 and goes, oh, I know what that is, and I know where it goes. So that label, that labeled packet comes over here. Again, if we were to look at the destination IP address, it'd be 10.1.1.50, we'll just say. And on the front of that, it puts the label in there that says this is going to label 53. When this router gets it, he pulls open his little LFIB, label forwarding database, and all that really says is, okay, if you see label 53 on your side, that's going to end up going to this router, and we're actually going to pop the label off. Huh? I know some of you are like, okay, I think I was kind of following until you said pop the label off. Why are you popping the label off? That's actually the technical term, by the way, pop the label. Because this guy is connected to the end user. Does the end user have any idea what MPLS is? Probably not. This is a service provider technology. It typically stays in the cloud. There's exceptions to that rule, but for the most part, our customers just know that the service provider uses MPLS. They don't really know the intricate details about it. Nonetheless, we don't want to give them a packet with a label on it. We want to give them a packet with an IP address because that's what our customers understand. So this router will have the packet received without a label. Now, you might say, well, why do you do it that way? I mean, why don't you send it with a label and let this guy pop it off as it sends it out to the customer? Well, good question. People who created MPLS asked that same thing, and they actually said, we want to optimize it. This is where this term PHP comes in. The penultimate hop popping. Penultimate pop hop, or and now I said it backward. Penultimate hop popping, right? I said that the right way. Okay, so first off, what is penultimate? I know when I saw it, I thought, well, this is Evernote, right? Isn't that something Evernote has as one of their like their apps or something? Penultimate means, if you look it up in the dictionary, next to last. Meaning, for instance, I have 5 children right now. Matter of fact, right before I recorded this video, I was eating dinner with them, and I sat down. I said, Solomon, because we have our, well, right now we have 5 kids. Solomon is 1.5 years old, right? I said, Solomon, you are my penultimate child. And all my kids go, what does that mean? I said, that means the second to last. Everybody got that? Everybody say penultimate. All my kids said penultimate, second to last. So Solomon is my penultimate child. Because he is child number 4 of 5 currently in my list of children. So right here, penultimate hop popping is an optimization technique. It says second to last router. So router 3 knows it's second to last. Why? Because router 4 tells it that I don't have a label for 10.1.1.0 because I'm not enabled for label switch routing. I'm not enabled for MPLS, if you will, on the interface going to that customer. So he says, you know what? Pop that off for me. Otherwise, the packet gets to router 4, it has to do a LFIB lookup, meaning looking in its label table, pop it off. Then it has to do a FIB lookup, look in its routing table to figure out where it goes. So instead, the people who created MPLS said, let's optimize it. Let's have the penultimate router. Have I solidified that in your mind enough? Because it's used all the time in MPLS. PHP, penultimate router. The second to last router is the one who pops the label off. So when it hands it off, I need another color, hands it off to this guy right here, he just does a routing table lookup. He doesn't have to look at the MPLS label since he is just routing it off to this customer in the end anyway. Okay. So we talked about edge label switch router. We talked about label switch router, just some of the terms. We talked about the penultimate router, PHP, the performance game. We talked about the FIB now, kind of in passing, which is the routing table. That's forwarding information base. And then we talked about the LFIB, which is your label table. It's essentially how the router knows to route the labels. Now let's expand. The FIB has been around, the forwarding information base has been around since the dawn of routers. It is a cached version of the routing table, which is populated via routing protocols, or I guess you could put in there if you're small, static routes can populate the FIB. It's how the router knows where to send packets based on IP address information. The LFIB is the new one. That's the MPLS world, the label forwarding information database, which is the locally significant MPLS label table. So I've put all these little labels right here. If I were to go onto an MPLS router, and I'll actually show you this in a little bit, you can look in and see the LFIB. And it will say, okay, well, I've got, when I see this packet with a label of 53, then I need to send it out interface Ethernet 0 with, and retag it with a label of 62. Right? And if I see a packet come in with a label of 10, it needs to go out serial 0 with a label of 115. Right? So that's what this LFIB table is. That's why this MPLS world is so optimized, is after the packet, go back to my little diagram I had before, it comes into the router, it sticks the label on it, and the label is actually for the next router in the chain. It says, I just received 10.1.1.50 as the destination, and router 2 told me that 10.1.1.anything actually gets a label of 53. So when the packet ends up getting to router 2, this would be router 2's LFIB table, looks at his LFIB table and goes, oh, I just got packet 53. Again, I'm not even looking at my IP routing table at this point. I know I need to send that out Ethernet 0 and change that label from 53 to 6 or to 115. Why? Because router 3, who's over here, told me that 10.1.1.0 is actually a label of 115. So router 3 would have a little LFIB table of its own. That's why I'm saying locally significant. These labels can be reused. They're dynamically generated. But router 3 gets 115 and says, oh, okay, well, in my LFIB table, 115 actually has a destination of serial 0/0, and I'm going to pop it because I happen to be the what? Who am I? Come on. What child is he? Penultimate. I am the second to the last router in the chain. Router 4 has told me he is connected to that customer on 10.1.1.0, so I want to send it to him without a label. Is it starting to get a little more material behind it, a little more meat there? So how does this label table thing work? Well, there's a key element called the label distribution protocol. Think of this as the routing protocol of MPLS. So these routers, as soon as you turn on MPLS, as soon as you turn on labels, they look at their routing table and generate a label for each one of them. So 10.1.1 gets this label, this label, this label, this label. It creates its own little label database that it locally has, and then it forms neighbor relationships using a multicast address 224.0.0.2. It says hello, just like a routing protocol. I am your neighbor, and I would like to let you know that my label for such and such is 24. So the neighbor says, okay, that's great. By the way, my label for 10.2.1.0, I just kind of abbreviated my little conversation, is pop. I don't have a label because I'm connected to 10.1 or 10.2.1.0. That's the customer. So please pop label. So again, this guy in his little LFib says, oh, okay, if I want to send a packet, are you getting this, right? I'm kind of circling around and hitting this concept because it takes a little bit to soak in, but that's how the labels work. All right, well, at this point, we've seen a lot of MPLS concepts. Let me kind of put them together into a congruent, systematic flow, labels in action, then we'll look at the configuration. What happens when we turn on MPLS on a router? First thing is it generates labels for each network. So let's say up here we have network X, right? So this is going to be in this router's routing table, network X as a what? Directly connected network, right? It's right there. And you'll probably have a routing protocol where they're advertising that. So everybody else has a routing table that says, well, network X is this way and network X is this way. This has nothing to do with MPLS other than we know that we have to have a base IP routing table. MPLS isn't the IP protocol. It takes the IP protocol and helps it be faster or more efficient by adding these labels to it. So this guy might say, okay, network X for me is 50. This guy might say, well, network X for me is 63. This guy's like, well, for me it's 777, right? Again, these labels are just randomly generated. Then they use the label distribution protocol to tell each other about that label that they've assigned. So this router will say, hey, by the way, network X for me is 777, right? Now, by the way, you might look at the packet flow and say, well, this router never even has to go to that guy to get to network X, right? True, but he still does it anyway. So this guy builds a little LFib database which says if I reach network X through that neighbor, then I'm going to put the label on it of 777. But what it really cares about is what this guy is telling it. This guy says, hey, to get to network X for me is pop. Now, who remembers what that means? That means don't send a label because this is not enabled for MPLS, so I know that I want you to pop that label. Don't send it to me with a label because that's, I'm going to have to pop it off anyway. That's that PHP, right? The penultimate hop popping. So this guy knows pop the label before it's sent. So it's not very exciting. So let's go somewhere further. Let's say somewhere further in the network was network Y, right? This guy might assign network Y 82, right? So sorry, or this guy. So he says network Y for me is 82. This guy says, okay, well, network Y for me is 91. This guy says, okay, network Y for me is 153. So again, it's in the routing table across the board. They've got all these MPLS labels. So they'll exchange it. So router 3 tells router 2, hey, if you ever want to reach network Y, then go ahead and put the label on it 82. Again, this guy builds the LFib saying, okay, well, I will go ahead and put in my little table that if I want to reach network Y, and I'm going in your direction, router 3, then I'm going to put the label on it of 82, right? And if I'm going to reach network Y, and I'm going in the direction of router 1, we'll say right here. Again, even though network Y is not reachable, they still advertise their label to each other. He says, I'm going to use 153. That way we don't just have a pop is the only thing that we see. But you get the concept of that, right? So these guys are building this LFib. So the pop is advertised for the last router in the system to the penultimate router. That's what I was just showing you right here. And the MPLS network reaches the steady state once all these labels have been exchanged. It's known as MPLS steady state. But know that no downtime is happening during the LDP convergence. So while they're exchanging all their labels, we're forwarding as normal. We're just using what way of forwarding? The FIB, right? The forwarding information base. We're using normal IP as a non-labelish routing. So MPLS just then adds the label to it, and then we go to steady state and start doing MPLS routing. All right, it's all led up to this point. Here's what I have in my mad scientist lab. 3 routers, XR1 running iOS XR, with a number of loopback interfaces, all part of the 10.223.x networks, so 10.223.0123, that kind of thing, connected over a, I think, Ethernet connection to router 1, a normal iOS router, just kind of acting as the intermediary between router XR1 and router 2, who actually has a number of loopback interfaces himself, 10.224.x.x, /24, so 10.224.111. Now I said 1, 2, 3, 4, 5, etc. So what I've got going between all of these routers is OSPF, just to get a little network scenario going, and then we're going to enable MPLS on top of it. So before we enable MPLS is one command, so I've got to build this up, right? Let's do a show route IPv4 on the XR1 router. And you can see there's our OSPF routes being learned from the other side of the connection from Gigabit Ethernet 0101. I'm going to bring player 2, router 1, into the picture, do a show IP route over here. And he should have the most OSPF routes because he's learning about the 10.223s and 10.224s from both sides of him. And then, of course, on the far side, we have router 2. Show IP route, and we should see the only OSPF routes are essentially the far side, 10.223, as well as maybe the WAN link between router 1 and XR1, right? Everybody good? Good. Let's go router by router. I'm going to go into router 2, go into global config mode. The interface connecting from router 2 to router 1 is actually serial 0/0/0, and this is going to be relevant. 000, because we've got to enable it on a per interface basis. This is serial 2/0. This is fast Ethernet 1/0, and this is gigabit Ethernet 0101, right? So we've got them for our reference. I'll go under serial 00, MPLS IP. That's it. Once you do that, LDP is already running. It's generating labels for every single route. So let's just go interface by interface. We'll do interface serial 2/0 on router 1, MPLS IP, and interface fast Ethernet 1/0, MPLS IP. Finally, let's hop over to XR1, which everything's different because it's iOS XR. We're going to go into MPLS LDP from global configuration mode. And then from here, we will enable it on a per interface basis. So I'll say interface GI 0/1/0/1, right? So that enables that interface for it. Let's commit that configuration. And we should see, you can see an LDP neighbor already coming up. Oh, there's our other one. That's the iOS XR coming up on router 1. And we are using MPLS. That's it. Seriously. So let me prove it to you. And then I also want to answer a question that may be cycling your mind. You might be thinking, well, wait a sec. Don't we have to enable MPLS on these loopback interfaces too? No, actually not, because this is the endpoint. So this makes the router 1 the penultimate router for both sides of these connections, right? It's going to do the PHP, penultimate popping, because this guy's going to advertise that I have these networks via OSPF, right? And via LDP, he's going to say, pop it. I don't need a label when it comes here because I am the endpoint. Does that make sense? So let's look at router 1 first. It's probably where the most action is going to happen. Let's do a first show MPLS LDP neighbor. Big command right there. And I'll be able to see that I have 2 neighbors, one here, 10.224.6.1. It's kind of its LDP identity, the highest loopback interface that's on that XR1 router. As well as, you can see down here, 10.223.1.1, which is the router 2. It has formed a neighbor relationship. And you can see I have bound these addresses to the LDP identity. Essentially, I've received these and labeled these from the other side. So I know, you're like, but what label is it? Let's do that. Show MPLS forwarding table. Watch this. Come on. Come on. Look at this guy. Not much happening. He's gone through and actually assigned labels to each one of them. Router 1's like, okay, 10.223.1.1 is actually label 16. 10.223.2.1, label 17, 18. Now, you see how it's doing it. It's just kind of starting from the beginning and adding them up. But then it says, okay, when I send it out to my neighbor, which is going out these individual interfaces, what am I going to do? I'm going to pop it. Why? Because I'm the penultimate router. That's what I do with is pop labels as I go from router 2 to router 1. So let's look at router 2. A little more action coming there. We should see some labels at least for XR1. Let's do show MPLS forwarding table. Probably my favorite MPLS command. Yeah, you can see right here the 10.223.112131, all these routes coming from where? XR1, right? These are behind XR1. And it's saying that I've assigned it the local label 16, and I have the outgoing label, meaning router 1, get the perspective here, router 1 has told me that if I want to communicate, I'm going to put the shim, the label, in front of the packet going to 172, or 10.223.1.1. I'm going to put the little shim 16, put the label in there as well. Now, I know it might be confusing. You're like, why are these the same? Well, it's because they're the same iOS. They're the same router, the same number of routes. I mean, we've got a lab environment. If we had, for instance, routes on router 1, well, let's just say beyond router 1, maybe from other routers that were coming in, something to make it different. You know what I mean? Right now, router 2 and router 1 know about the same routes. They learned them in the same order, same. So naturally, they're going to use the same algorithm and generate the same labels. That's okay. These labels are locally significant. When router 1 gets a packet labeled for 16, it looks at its label table, right? And it's go, oh, I just got a label 16. What do? I pop it, and I send it out fast Ethernet 1/0 to the next hop 172.16.1.1. Tell me that's not cool. Oh, we forgot XR1, right? Let's come back here and do a show MPLS. They're always slightly different. LDP bindings. Let's take a look there first. Okay, so this is showing all of this. It's not as pretty as that forwarding table, but you can see, for instance, 10.223.1.0 local binding imp null, meaning I pop it. This is saying this is my network, so I'm labeling it. I put a little label on it as it is a null label. So I'm going to advertise essentially. Hang on, there's a better command that we can use. Show MPLS. It's forwarding instead of forwarding table. We had forwarding. Same thing here. But you can see XR1 started its labels from 16,000. Now, why do we never see that on router 1 and router 2? Well, because router 1 only gets the pop, right? Because XR1 doesn't want it to send a label in. It says pop it. And then router 2 doesn't care about XR1's label because it's not a neighbor of XR1, right? It's just labeling for the next hop, which is going to be router 1 in this case. But anyway, if we did have other neighbors of XR1 that wasn't pop routes, we would actually see these labels showing up in their forwarding table as well. Ta-da! As with most things Cisco, it is heavy in concept, very light in terms of configuration. The configuration is simple once you know how it all works. MPLS using LDP just from the beginning, automatically building the label table, advertising it to its neighbor, making it all happen. We have seen what MPLS is. We have seen an MPLS packet. By the way, you will hear a lot of people refer to MPLS as a layer 2.5 protocol. In the OSI model, because it fits right between layer 3 and layer 2. So you'll hear a lot of, people just argue about things on the internet for no good reason. Let's post a blog and just start a dispute about what layer MPLS is at. So anyway, most people just say, it's layer 2.5, right? So we looked at the dissecting MPLS packet, looking at the shim in the header, and finally, we saw labels in action. I hope this has been informative for you, and I'd like to thank you for viewing.